My name is Daniel Cruz. I'm an application engineer for ReliaSoft products here at HBM Prensia. And I'd just like to restate once again, if you have questions at any point during the presentation, please type them into the Q&A panel. I'll try and get through as many as I can in the time that we've got at the end. I really appreciate you guys paying attention, staying engaged, and asking questions. Is a great way to do that. So this webinar has a really long title, and it really boils down to applying reliability techniques to batteries. And the disclaimer here is that I'm not a battery chemist or a battery physicist or battery expert, but I've tried to do a good amount of sort of battery-specific research and preparation to this to make sure that everything I touch on from a reliability perspective is useful to those of you who are battery chemists and battery experts. So just a quick introduction for those of you who aren't familiar. Prensia, HBM Prensia is an umbrella brand for ENCODE software and ReliaSoft software. And my job is more on the ReliaSoft side. And my time is pretty evenly split between our offerings of training courses, reliability training courses, demos of our ReliaSoft software, and post-sales support, implementation, and consulting. So Prensia more broadly offers a host of these different training courses, both conceptual and software focused, support and consulting to accompany our engineering software in the reliability and durability domains. And ReliaSoft and ENCODE are both suites of software with many different tools within them. And this webinar, we're going to focus on a particular challenge, namely electric vehicle battery life, and how you can use some ReliaSoft tools, primarily Weibull++, to help characterize it. So here's the challenge. Here's the problem that we're trying to solve here. We've got increasing electrification in the automotive industry, and now we've got this big new component that we've got to study and warranty, the battery pack. And for any type of battery, a big concern is how long is it going to last? For an electric vehicle, what's the range? That's a huge concern for EV customers. And batteries lose capacity, lose range over time. So characterizing the life, the length of time before its capacity dips below a certain point is really critical for pleasing our customers. Also for satisfying regulatory bodies and even environmental agencies. How long is this pack going to last before it needs to be recycled or scrapped? So ensuring that our batteries keep their range and perform to expectations for a long enough period of time is really important for our company's success. And the automotive industry is converged on this 8-year, 100,000-mile standard. While I'm going to focus on automotive and this target, the things I'm talking about apply to other industries where you've got batteries in your products, consumer electronics, electrified flight, right? There's an ever-increasing number of products with batteries as well. And in any case, what we're doing is we're guaranteeing that if your battery pack fails in a given time period, so let's say 8 years and 100,000 miles, we'll replace it. And that replacement is really expensive. Battery packs are really expensive, and we want to minimize how many replacements we have to do. What's considered failure varies a little bit from manufacturer to manufacturer, but typically includes, complete failures. The battery pack is dead or caught on fire or something like that, as well as degradation beyond a certain point, meaning like if you lose 40% of the capacity, 40% of the range before 8 years or 100,000 miles, you get a replacement. So that's our challenge, and it's really difficult. We have some limitations here that make meeting that challenge a further challenge, right? Namely that 8 years is much longer than our entire design cycle for an electric vehicle, right? We can't, even if we had an 8-year design cycle, we can't spend the entire time testing batteries, right? We've got other stuff that we've got to do during that design cycle as well. And on top of that, testing a whole battery pack is really, really expensive. The pack itself is expensive, the fixtures, the test time, really expensive. And finally, even if we took, 5 whole battery packs, tested them for 8 full years and got no failures, that doesn't mean that we have 100% reliability, right? We could have very, very good reliability, or we could have very bad reliability after having observed that test result. And so, these are challenges that we face here, but the good news is that none of these challenges are unique. None of these are unique to batteries. These kinds of problems are the ones that reliability engineers have been faced with and have been addressing for all kinds of systems, including batteries, for some time. So, like I said, I'm not a battery expert, I've tried to inform myself as best as possible about battery life, prediction methods and failure modes, etc. But my goal with this webinar is to impress upon you, those of you who are interested in batteries, the applicability and usefulness of reliability analysis methods, the kind of bread and butter reliability analysis methods that we use, and show you what that analysis could look like in ReliaSoft software. So some of the battery-specific considerations are these, right? We've got many different failure modes to think about, some of which are well understood, some of which are kind of active topics of research. But we've got a couple ones, namely capacity loss type failure modes, right? Where the battery is losing capacity over time, either due to repeated cycling, charge-discharge cycling, or time at level, time at a high state of charge, which results in reduced capacity. But there are a whole host of chemistry, physics related battery cell failure modes, and I don't pretend to know what all of these are, but I expect that someone within your organization, if you're producing batteries, is going to know which of these failure modes are really of interest and what these crazy looking equations mean. And of course, we've got other failure modes to consider besides these sort of chemical capacity loss type failure modes, mechanical failure modes, for example. The battery pack is not 100% batteries. It consists of all of these cells and modules that are connected together. Those connectors are susceptible to fatigue. And it's also a pretty large structural component in what's ultimately a vehicle, right? And that structure is susceptible to fatigue. And that's something we need to consider as well. On top of that, there's auxiliary systems that support the battery pack. So cooling systems, control systems, those could also fail, and that would result in battery pack failure. So we've got all these different failure modes, and many of them have been or are being carefully studied by people with deep knowledge of the physics of failure here. So the battery chemists, material scientists, physicists, etc. And you could find all kinds of interesting models that predict life as a function of some stressor or some combination of stressors. In the same way that my background's in mechanical engineering, you might predict fatigue based on a combination of stress range, mean stress, surface finish, stress concentration factor, those kinds of things, right? And these models are definitely going to be useful for us. But first, I'd like to kind of take a step back and look at what the output of something like this is. The output is typically that we have a single number, a single life estimate that we produce as a function of some of these different stressors. So maybe depth of discharge, state of charge, temperature, voltage, some other things according to some physics explanation that we've come up with and tested. But we get a single number. So let's say we use this equation, we get a number 12.7 years is your battery life. Well, what does that really mean, right? If we know that our target life is 8 years and our formula tells us it's 12.7 years, does that mean that we have 0 failures? Not really, right? And furthermore, if we've got 2 failure modes, let's say we've got one failure mode characterized by one equation and one characterized by another equation, right? And we say one of them has a life of 12.7 years against failure mode A, and another one has a life of 9.9 years against failure mode B. What does that mean for the whole battery, right? How do we combine our estimates from those different physics-based models? So this is kind of the remaining challenge here. We've got these in my research and preparation for this webinar, I found that there's a lot of these physics-based models. There's a lot of research going into this, which is good. But that life estimate, 12.7 years, we don't know what it really means in terms of reliability. What percentage of our battery packs are going to fail if we have a predicted life of 12.7 years and a design life of 8 years, right? Furthermore, how many samples do we need to test under what conditions, or what kind of test can we run in order to verify that we actually do see that reliability behavior, that our reliability behavior is acceptable? And then, given the results of different tests, given the results of different failure mechanisms, how do we combine them to get an understanding of the whole pack, not just one equation or several equations outputting numbers that are greater than 8 years, perhaps? So the first building block that we're going to talk about here first reliability building block here is life data analysis or Weibull analysis. And this is kind of, like I said, the bread and butter tool that you'll use in ReliaSoft Weibull++. And this boils down to this kind of axiom that identical parts, if we've got identical battery cells under identical conditions, they're going to fail at different times, right? If we get a life estimate of 12.7 years based off of some physics model, we don't expect every single cell to last exactly 12.700 years and then fail. We expect some spread about that 12.7 years. And Weibull analysis, life testing is all about characterizing that spread, recording failure times and characterizing that spread. So that lets us go from the life is going to be 12.7 years to something like these couple statements here, right? We have at 8 years, somewhere between 91 and 99% surviving. That's a statement we can make using this use level life distribution. Or we could say the B5 life, the time at which we'll see 5% failures, maybe 5% is our acceptable threshold. It's 8.5 years. That's a statement we can make using this distribution. Or we can say, perhaps, the reliability at 8 years is greater than 90% at a 90% confidence level. It's another statement that you might make. And so these answers are a lot more useful to us in understanding what's actually going to happen at 8 years, with the caveat that we require failures, right? We require failures to build this distribution, or failure times. So that's why I refer to this as a building block, because this distribution, this little blue curve here, this is kind of the end goal that we have in mind, because it lets us get these directly interpretable answers. So we're going to talk about a couple additional tools that you can use to get there without having to test for 12.7 years and get a bunch of failures. The first of those I'm going to talk about is degradation analysis. So this is something that, again, is a standard reliability analysis. And basically, it's tracking some degrading quantity. So if each of these lines represents a single battery cell, right, then the degrading quantity here could be capacity. We track that capacity over time and project when it will reach our failure threshold level. So in this particular test, these points are our measurements. None of our battery cells have reached the failure threshold, but we're able to project approximately when they will and use that to build our life distribution. So that allows us to do our life data analysis without any observed failures. And in my research for this, I found that batteries in particular struggle with finding these degrading quantities, or at least finding degrading quantities that are well behaved. So for example, you might see something that decreases, then increases and decreases and has like a knee and then decreases more rapidly. But I also found a couple people, a couple of really smart people who would come up with some clever ways to measure something that smoothly degrades in this pattern. So I believe this is possible for batteries. There's a citation I have in my last slide where they have an indirect capacity fade measurement technique. And I believe this could be applied to that. And this allows you, again, right, without having gotten failures, run a test without any failures, but still come up with those answers that we're interested in, right? This percent will fail at 8 years. Another tool we can use, and one that you might be a little bit more familiar with in the battery space, is accelerated testing, where we take advantage of those physics models. So like I said, that type of research that people are doing is really useful for us because they are characterizing how battery life changes with some of those stressors. So let's say you've got temperature or depth of discharge, and you're interested in varying those in a controlled way to understand what that, in a shorter period of time, what the reliability behavior is like at the use condition. Well, you can do some research, and I've got citations for these as well, where you can find, okay, battery life varies with temperature following an Arrhenius relationship, or if we're varying depth of discharge, right, a power law relationship, or there's one citation I've got here that varies both and proposes a generalized airing model, right? These equations are equations that are in the software that you can use to increase the stresses in a controlled way, and through your understanding of the physics of what's going on, project back to the use condition, get that same use condition distribution. So we can test in a short period of time by cranking up the temperature and depth of discharge, and understand what that means in terms of when failures will occur, what percentage of failures will occur. Something that I know also takes place in the battery world is design of experiments, right? Maybe we don't know which stresses are really the most important ones for designing an accelerated test. Maybe we're still in that phase of developing our knowledge of which factors are most critical. And we could do a design of experiments. This is also included in Weibull++. There's a design of experiments module, and you could say, okay, here we vary depth of discharge, current, state of charge, voltage, and temperature. And it tells us the most obvious effects are, the most obvious influencers of battery life are the depth of discharge and the current, for example. So maybe we take those now and design an accelerated test based off of that. So we've got a couple tools now in our toolkit that all lead us to that use level life distribution. And we now can get those probabilistic estimates that are really useful, right? Because if we just have the projected life is 12.7 years, we can't really say what that means in terms of money. Whereas if we have a probabilistic model, like our use level life distribution, like our Weibull distribution, we can estimate, for example, warranty claims and directly relate that to the money or the cost of reliability. So, for example, if we find that our current battery pack design is going to result between 2 and 8% failure at the warranty period, 8 years, then we can multiply that by a replacement cost and units sold to literally quantify this is what we expect with our current design if we launch to expend in terms of warranty. Furthermore, you could say, well, if we could get rid of this mechanical failure mode in the module level, right, we would increase our reliability by 2%, right? And 2% corresponds to this much money, X dollars over, however many thousand units. So that probabilistic model really, really helps us communicate this beyond, we as engineers, we understand the benefits of this type of reliability analysis, but this really helps us communicate it to non-engineers, to our managers or people making decisions. To justify, test activities, analysis activities, R&D activities. Furthermore, once your product's actually in the field, perhaps shortly before your product's in the field, you can use that same probabilistic model combined with the age of units that are out there to come up with the plot on the right, which is an expected failures plot per month. So this is telling us we're expecting, between 280 and 300 claims in September. We're expecting between 310 and 315 claims in December, right? This type of plot can also tell us on a month-by-month basis or a quarterly basis, right, how much money we're going to expend due to the reliability characteristics of our product. So this is why we're doing this kind of reliability analysis and the advantage that we get from this reliability analysis on a failure mode level. And so I hope this gives you a good sense for how you get to those use level life distributions and why you want to do that. And I thought it would be helpful at this point to show what this actually looks like in the software. So here's an example where we tested battery cells, this is at the cell level, under elevated temperatures. So based on expert knowledge, preliminary testing, perhaps some design of experiments that we did, we decided we're going to elevate the temperature to speed up the test and characterize this particular failure mode. So I'm going to show you how you can analyze this test in Weibull++'s accelerated testing module, what that looks like, what kind of outputs you get. So this is the software. Okay, we tested 30 units. Each row corresponds to 1 unit. And we basically tell the software, this is how long we tested it for. This is whether it failed or didn't fail. And this is the temperature that it was tested at. And it doesn't have to be temperature. It could be, like we said, depth of discharge, some other battery-related stress. And then we simply fit a model, and it tells us now at the use condition, what is your probability of failure versus time curve. So this curve is based off of extrapolating back from the high temperatures we tested at to the use condition temperature, and it tells us that at 8 years, we're going to see about 2% failure. Right? And this works by creating what's called a life stress plot here. We tested at 3 different temperature levels, at 340 Kelvin, 325 Kelvin, 315 Kelvin. And this model tells us at every temperature now, including our use temperature, which is going to be somewhere over here, what our expected life is, and furthermore, what the spread of life is. What is our probabilistic model at different use conditions? So, we understand this now. You can copy paste these plots as images, put them into PowerPoints like I've done for this webinar, right? You can report out variable results here. So I've created a table here where it for different ambient temperatures, what probability of failure I can expect, as well as a 90% upper bound, right? So this uses like kind of an Excel style formula here to use the model that I've created, as well as some additional information in the table to give me my probability of failure. This is really useful and user friendly for reporting out these results and making your decisions based off of the analysis that you do. So this is just one test, right? Realistically, we're going to have multiple failure modes. We're going to have multiple tests that we run, and we've got our battery pack. We've got perhaps cycle aging, calendar aging, mechanical failure, cooling system failure, etc. And using these tools, we can get a life model that tells us the probability of failure for any of these failure modes at our time of interest, 8 years or 100,000 miles. So that's already a huge advantage, right? Now we go from a single number to a probability that translates more directly into costs and intelligent engineering decisions. But now let's say we want to go one step further, right? We want to say, okay, we've got these different failure modes. What does that mean for the whole battery pack, right? So let's say we've characterized our 4 main failure modes, and we've got them at different levels of the battery pack hierarchy. So we've got 2 failure modes at the cell level, calendar aging and cycle aging, failure mode, the module level, where the connectors are susceptible to fatigue, the failure mode at the pack level, where we've got structural fatigue, perhaps. So we can characterize each of these with those reliability tools that we've just learned about, and we can combine them. We can roll up the cell level to the module level to the pack level in what's called a reliability block diagram. So this is using our software called BlockSim, right? This reliability block diagram represents a single battery cell where we're susceptible to both cycling capacity fade and calendar capacity fade. And so we could take these 2 blocks, which represent these models that we built, and combine them and calculate the results at the cell level. We can then go to the next level and say, hey, okay, we've got this many cells in a module, as well as a failure mode at the module level that represents connector fatigue. And then we can go a step further and say, we've got this many modules within a pack, and some pack level failure mode, so cooling system failure perhaps. And the software resolves the math for us and gives us a nice, smooth probability of failure versus time curve for our whole system, a system reliability equation that we can now analyze. So that lets us answer the question, do we meet our reliability target at the system level? So if you look at the plot on the right, this green line is our system probability of failure curve, and this red cross is our target reliability. So you can see that our probability of failure is too high. We don't meet our target. And if we had just looked at the constituent models, each of those would meet the target, but because it only takes one of them to cause a battery pack failure, we don't meet the target at the system level. So 20% failures at 8 years is too high. So we might want to know now, what should we prioritize, right? Which failure modes are the most important ones to eliminate to get that number up? And what would the reliability be if we eliminate them? Like I mentioned before, you could come up with a dollar value attached to the elimination of a failure mode using this methodology. And so that system reliability equation that the software has found could tell us exactly that. So how sensitive is the system reliability to that mechanical failure mode at the module level, right? This bar chart here is something called reliability importance, which is exactly that. And it tells us, okay, in this kind of generic RBT, block number 4 is the biggest bad actor. So failure mode number 4 is the biggest bad actor that we should target. Additionally, we can go the other direction. So let's say we need to hit a 95% reliability target. We can allocate that to our different, to the module, to the cell, to the different failure modes, even taking into account how expensive reliability improvements are. So let's say it's relatively cheap to improve the fatigue type failure modes, whereas it's relatively expensive to improve the cycle life type failure modes. We could tell that to the software, and that's what this table on the bottom here is. And it'll essentially tell us, okay, based on that, based on this failure mode being hard to eliminate, based on your current reliabilities, this one should remain approximately the same, and you should really focus your efforts on number 4 and number 1 here. So maybe you should really focus your efforts on these 2 fatigue type failure modes. So this is a really useful tool to get high level understanding of what is all this analysis that we've done? What does this really mean at the system level, and therefore, from a cost perspective? So it's a lot of tools, right? I've talked about a lot of tools here. So I want to take us back here and summarize in just a couple sentences. The main point here is that existing reliability techniques really help us understand the range of possible outcomes, not just a single number, which is really useful for batteries, for all kinds of products. We can use that domain knowledge and our understanding of those physics models to inform our modeling of that spread of outcomes, right? That spread of outcomes, that probabilistic model, is really valuable to us because that probability of failure that we get out of it is directly related to cost. It can be used to justify, analysis activities can be used to justify, well, we need to test this many samples because if we don't, we run the risk of, $1 million of warranty costs. And so once we've got that, we can go a step further. We can combine those models to get overall reliability at the system level, at the pack level, and to prioritize which failure modes are really the most critical. You can even take into account, how expensive different failure modes are to address. And so we go from, just a formula that tells us what the life is, to modeling the spread, getting a probability of failure, understanding the cost, and understanding the system level reliability behavior.